Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to calculate the standard free energy change from the cell potential. So let's get into this. So I'm going to do a couple of practice problems. In this video I'm going to go over one problem, and in the next video I'll go over another one. So in this video we have a reaction, and they're asking us to use the electrode potentials, the tabulated electrode potentials, to calculate the standard free energy change of the reaction. And the reaction that we're given is this one right here. So we're taking solid iodine, putting that in an aqueous solution of bromide ions, and then we're going to produce the iodide ion along with bromine liquid. Okay, so first thing we want to do is we want to break this up into our oxidation and reduction reactions. We need to figure out what's being oxidized, what's being reduced. And then when we figure that out, we could look up the electrode potentials and use those. So the reason we want to find out what's oxidized and what's reduced is we got to remember our mnemonic here is a red cat and an ox. So red cat and an ox. So this is a mnemonic device to help us remember that the cathode is where reduction occurs and the anode is where oxidation occurs. So if we figure out what's being reduced, what the oxidation reaction is, and what the reduction reaction is, then we can use this equation here to figure out what to calculate the standard cell potential. And then there's another way you could do it that I'll explain in a moment that's just as useful, if not maybe more useful. Okay, so let's get into this. So we have iodine. Iodine have an oxidation state of 0 because it's a pure element in its standard state. Bromine is a monatomic ion, so its oxidation state is the same as its charge, -1. Same goes for the iodide ion with a -1. And then bromine here, liquid, that is the standard state of bromine. So that is going to have an oxidation state of 0. And so if we write this out, so our iodine is going from 0 to a -1. So 0 to -1 means that iodine is picking up electrons. It's gaining electrons. So that means it's being reduced in this reaction. So if we write that out as our reduction, right? So this is going to be our reduction. So iodine is going from I2 solid, and it's going to negative. So it's going to be, this means that it's picking up 2 electrons, and it's going to produce 2 negative iodide ions, aqueous. And then that means that the bromine is being oxidized. So we'll write that out. And we can see that by it's going negative, going from negative to 0. So it's losing negative. It's becoming more positive. So it's losing electrons. So that's oxidation. So that means that here we're going from, oops, let me fix this here. And so that's going to be 2 Br minus aqueous. And then that's going to go to, draw my arrow, that's going to go to Br2 liquid plus 2 electrons. And so now we know what's happening at what's being reduced, what's being oxidized, the reduction and oxidation reactions. And so we know that according to our mnemonic, a red cat means that reduction is happening at the cathode. So here, this is at the cathode, and therefore this is at the anode. So now we can calculate our standard cell potential. by using this equation here. So we can plug that in using these values here. So here, let me just kind of separate this out and explain what this is here. Probably wondering. This here is the reduction reactions that I would get from the table. So I go to my electrode potential table and look at the reduction reactions, and then I'm comparing bromine and iodine. So this is the order that they're in. There's a lot more on the table, but I took these out and put them here. So you'll see in the table that iodine is lower in the table than bromine. So bromine being higher in the table is going to have a stronger, not desire, but a stronger tendency to undergo reduction. It's going to want to undergo reduction more than the iodine. And you can also see that from the fact that it's more positive. So if you remember the mnemonic device, neo here, let me write that down. So neo per. So more negative is oxidation. More positive is reduction. So here we have more positive, right? So this one's more positive, so it's going to undergo reduction. It's also higher in the table. So as you go from the top of the table, it's more positive. As you go down the table of the reduction reaction electrode potentials, it's going to become less positive or more negative, if you want to think of it that way. So here we see the potentials, and so we have this reaction. The reduction is this one here, and the oxidation is this one here. Okay, so that means that this one is being flipped according to this reaction here. So we can already tell that this is probably not going to be spontaneous because it's going in the opposite direction than that we would expect. So we would expect that the delta G is going to be positive in this case. But let's go ahead and calculate it out. Okay, so we got everything set up. So now what we're going to do is there's two things we can do. We can use this equation here that the standard cell potential is equal to the electrode potential at the cathode and minus the electrode potential at the anode. This looks like a J. It's not a J. It's a semicolon. I don't know if that looks any better. All right, so we can plug that in. So what I'm going to do is I'm going to write it over here and show you this way. So here I have the electrode potentials here of these two reactions. This is the iodine one is happening here. So this one is going to be at the cathode. So I'm going to have my E standard cell, the standard electrode potential of the cell is equal to the electrode potential at the cathode, which is this one, which is iodine. And I come here and I write, oh, that's going to be 0.54 volts. Okay. And so then I'm going to subtract the electrode potential at the anode, which is happening with the bromine here. So the bromine here, the E there is a positive 1.09 volts. And so now all I do is I subtract, and the answer I get is going to be a negative 55? Yes, 55 volts. So now I have my standard cell potential from these here. Now, the other way to think about this is think about adding the reduction and oxidation half reactions you add together to get the complete reaction. So that's why I have these written here. So these are the actual reactions here that are happening here. And so if I take these equations and add them together, right, I'll get my equation here. So I have these two reactants, the electrons, the two electrons on both sides are going to cancel out. I get my I2 solid plus my 2Br minus aqueous, and that's going to give me my Br2 liquid plus my 2I minus aqueous, and I get the same reaction as I did here. The only, these are flipped, but that's okay, it doesn't matter. I've got these as products, these as products, these as reactants, these as reactants. So what does this tell me? It tells me that if I add these two together and I get this one, well, I can then apply that to the electropotentials. If I add two equations together, two half reactions together, then all I do is I add their electrode potentials together. Now here's the trick though. Notice that bromine here is written with bromine liquid plus 2 electrons plus is going to give me 2 bromide ions and aqueous. But the way I have it written here for this equation, for the equation I am interested in, it is flipped, right? So the 2Br are on the reactant side, not on the product side. So when you flip the reaction, what do you do with the standard electrode potential? You change the sign, right? So if this equation here is a positive 1.09 volts, then if I flip it, it's going to be a negative 1.09 volts. So then if I write this here, so iodine stays the same, so that's going to be an electrode potential. I'll write it here. That's going to be the same as before, a positive 0.54 volts, right? And then this one's going to be that number there, but it's flipped, so we're going to change the sign. So this one's going to have an electrode potential of not positive 1.09, but a negative 1.09 volts. So when you add these together, you get the electropotential of this whole reaction, which is the reaction happening in the cell. So that would give you the standard cell potential. So here we get the same thing. It's going to be if I write down here, that means that if I write the standard cell potential is going to be equal to this one, positive 0.54 volts minus 1.09 volts. I add those together or I subtract them, however you want to think about it, and I get the same answer, negative 5.55 volts. I get a negative 0.55 volts for my E cell, which is the same number I got here, right? So I got that number here. So you can use this equation, or if you want to think about it in terms of if you figure out which one is oxidizing, you flip that one on the table, and in doing so, you change the sign. If it's negative, you change it to positive. If it's positive, you change it to negative, right? And then you add them together, which is essentially what this equation is doing, but it's not really showing you that. So that's kind of like why this equation works. It's because if it's oxidation happening at the anode, then basically you're flipping the equation around, and therefore you got to change the sign of your electrode potential. Okay, now that we have our electrode potential of the cell, we can now use this equation to calculate this standard free energy. So here's a standard free energy equation. That's going to delta G, standard free energy change, is going to be equal to negative of N, right? And N represents the number of electrons, the moles of electrons transferred in the reaction. So we can see here that we have 2 electrons here, 2 electrons here. That's 2 moles of electrons. So that's going to be a 2 for the N, right? A 2 for the N. And F is Faraday's constant. So we're going to add Faraday's constant. So that's going to be 96,485. And the units are going to be coulombs per second, or I'm sorry, per mole of electrons. So this is coulombs per mole. And we're going to multiply that by our standard cell potential, which we just calculated, which is negative 0.55 volts. So we're going to put that in here. So negative 0.55 volts. Okay, and remember, a volt is equal to joules per coulomb. Joules per coulomb. So that would be, if I change that, it would be joules per coulomb. So here the coulombs cancel out, and here I have moles of electron. The moles are going to cancel out, and I end up with joules, which is what I would expect for my delta G, my standard free energy change. So when I calculate this out, I get the positive 1.1 times 10 to the 5th joules. So that's my delta G. And again, you can see that it is positive, which means that it's not a spontaneous reaction, which is what we kind of predicted, because we saw that according to the electrode potentials, bromine should be the one being reduced if it's going to be spontaneous. But in this case, it's not being reduced, it's being oxidized. So that kind of indicated that it wasn't going to be spontaneous. And now we've confirmed that. I hope this was helpful. If you enjoyed this video, then please, by all means, like the video, share the video with your friends, hit that like button. Also, make sure you subscribe to my channel, hit that notification bell. Also, if you do, make sure you hit all so you can be notified by all the videos I put out. And finally, put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.